In this video, we are going to look at the second part of chapter 15 by looking closer at contingency tables and tree diagrams. So I want to show you in general with a contingency table, also called a two-way table if we just have two variables, but sometimes you're going to have more than that these inside cells here display joint probabilities or the intersection of two sets, okay? Whereas your margins have just simple probability. So this value here is the probability of event A occurring. Now, sometimes it's just raw counts or frequencies in here rather than relative frequencies, and you have to do a little bit of calculations. Let's take another look at the drunk driving situation. So police report that 78% of the drivers are given breath tests, 36% a blood test, and 22% are given both tests. So we've already looked at this scenario using a Venn diagram. I'm going to show you the same scenario, but we're going to do it by looking at it through contingency table. So some people take a breath test, and some do not, and some take a blood test, and some do not. So I'm told that 78% take a breath test, all right? So that's going to be actually the marginal. Okay, that's a simple probability. And 36% a blood test, and 22% do both. So that's your intersection, that's right here. And now you can use subtraction to get the probability of no blood test. It would be 78% minus 22 would be 0.56. No breath and blood test would be, well, subtract 0.36 minus 0.22 is 0.14. And what else do I know? Well, my probabilities have to add to 1, so that means 0.22 is remaining here. And this would be 0.64. So then I'm going to subtract 0.64 minus 0.56 to get 0.08 for right here. That would be the probability of no blood and no breath test. So now let's answer the questions. First of all, we are asked, are these mutually exclusive? Well, no, these are not disjoint. We have 22% who are given both. Now, to determine if the two tests are independent, we're going to use the idea that, well, the probability of one event, so I'm just going to go with breath. I could do it a different way, which I'll mention in a second. The probability of breath, given that I've also taken a blood test, has to be equal to the probability of just having a breath test. So how do I calculate the probability of taking a breath given I've already taken a blood test? You have this formula for conditional probability on your formula sheet. This is equivalent to the probability of breath intersected with blood divided by probability of just a blood test. So probability of breath and blood, that's a joint probability. That's right here. That's this one, 0.22. So I have 0.22 over the probability of just a blood test. So just a blood would be 0.36. Okay, and then I am checking to see if that's equal to the probability of just a breath test. But first, let's calculate what is 0.22 divided by 0.36. And I get 0.61. And then the probability of just a breath test, well, that was given information. That was equal to 0.78. Okay, so what's my conclusion? These two things are not equivalent. So my conclusion is the chance of having a breath test given a driver has already had a blood test is less than the chance of being given a breath test. Therefore, they are not independent. Now I'm going to show you how to use a tree diagram to calculate probabilities. So a tree diagram shows the sample space of a chance process involving multiple stages. The probability of each outcome is shown on the corresponding branch of the tree. And all probabilities after the first stage are conditional probabilities. One of the big questions from kids is often, well, when do I use a tree diagram versus a contingency table? So definitely when it gets more complicated with lots of stages, I definitely use a tree diagram. Sometimes both will work. So in example 7, Shannon hits the snooze button on her alarm 60% of school days. If she hits the snooze, there's a 70% probability that she makes it to her first class on time. If she doesn't hit the snooze and gets up right away, there's a 90% probability that she makes it to class on time. Suppose we select a school day at random and record whether Shannon hits the snooze button and whether she arrives in class on time. So we're going to make a tree diagram, and then we're going to use it to calculate some probabilities. So the alarm rings and one of two things happens. Either she hits the snooze, or I'm just going to say no snooze, meaning she gets up right away, right? And I'm going to add my probabilities right on the branches. So I typically write my word under the branch and I put my decimals, I always use decimals, above the branch. So it says she hits the snooze 60% of days, which means 40% of days she's going to get up on time. Our next fact would be if she hits the snooze, there's a 70% probability that she makes it to her first class on time. Right? So she's either on time or she's late. So 70% of the time she's on time, which would mean the remaining 30 she's late. So notice these two branches, each time it kind of branches there, it needs to add to 1. Okay, so she didn't hit the snooze. Sometimes she's on time, but sometimes she's still just late. Right? What percent? Well, it says 90% of the time she's on time when she didn't hit the snooze, so 90%, and that means the other 10% she's late. Now, before I start answering any questions, this is the nice way that probability works. I multiply my probabilities together. So as I go down my branches, I got 0.42. This would be 0.6 times 0.3 is 0.18. And then I have 0.4 times 0.9. Trace that branch would be 0.36. And 0.4 times 0.10 would be 0.04. Before I do anything else, I just check my sum. These probabilities out here better add to 1. It's a good check because if they don't, you've messed up somewhere and you better fix your tree, find your error before you go any further. Now each of these probabilities on the second branch is 0.7. This is a conditional probability. Specifically, that 0.7 would be the probability you're on time given you hit the snooze. And that was the 0.7. Whereas these probabilities out here, this is your joint probability or your intersection, the probability that you hit the snooze and you're on time. Understanding that big idea will help you with individual questions. So let's answer the questions about our tree diagram. Find the probability that Shannon hits the snooze button and is late for class on a randomly selected day. Well, these are your joint probabilities, so just trace it. Snooze and late, that's right, is multiplied together, it's the 0.18. What is the probability that Shannon is late to class on a randomly selected day? So where is she late? Well, she's late along this branch and this branch, so that's our 0.18 and our 0.04. So proper notation would be the probability that she snoozed intersected with late, plus the probability she didn't hit the snooze intersected with late. And we just said that was 0.18 plus 0.04 equals 0.22. We are going to switch directions now. We're going to reverse our conditions. So this was set up by the alarm rings and you either hit the snooze or you don't, and then we looked at the conditional probability. What percent of the time were we on time or late? given that we hit the snooze. This now says, suppose that Shannon is late for class on a randomly selected school day. What is the probability that she hit the snooze button that morning? So it's saying the probability she hit the snooze given that she was late. Okay, so we're like switching directions on our tree diagram. We're going backwards. How on earth are we going to do that? At first it might boggle your mind, but you can actually just use your conditional formula, which is on your AP formula sheet. So you're looking at the probability that you snooze intersected with being late divided by the probability of the second one, which would be late. How do we calculate that? Probability of snooze and late is right here. It's 0.18. Divided by the probability that you are late. Well, that's two separate things. Late was 0.18 and late was 0.04, so we just add the two together in the denominator. So this is 0.22 on the bottom. 0.18 divided by 0.22 gives me about 0.818. Now I give you a medical example next because it's one of the most important applications of conditional probability, and that's in the area of drug and disease testing. It says many women choose to have annual mammograms to screen for breast cancer after age 40. A mammogram isn't foolproof. Sometimes the test suggests that a woman has breast cancer when she really doesn't. This is a false positive. Other times, the test says that a woman doesn't have breast cancer when she actually does, and this is a false negative. Suppose that we know the following information about breast cancer and mammograms in a particular population. 1% of the women aged 40 or over in this population have breast cancer. For women who have breast cancer, the probability of a negative mammogram is 0.03. For women who don't have breast cancer, the probability of a positive mammogram is 0.06. We're going to construct a tree diagram with this info. So first of all, in this population, there are some women who have cancer and some who do not. It's 1% who do, 0.01. Unfortunately, 99% do not. But of these, we're testing all the women. And we're going to look at whether the test is positive or negative. And I'm just going to use a plus and a minus for these two scenarios. Positive versus a negative test. So for the women who have breast cancer, it says the probability of a negative mammogram is 0.03. So that would be this branch here, which would mean by my complement rule that this needs to be 0.97. Remember, they need to add to 1. For women who don't have breast cancer, the probability of a positive is 0.06. And by my complement rule, this would be 0.94 for the negative. Remember that this is conditional probability here. The probability that you have a positive test given you have cancer. Whereas down here, probability of positive that you don't have cancer, this would be a false positive right here. The next thing I want you to do is pause the video and multiply your probabilities together and confirm that they add to 1. When I do it, I do get a sum of 1. So what is the probability that a randomly selected woman has a false positive test? What does that mean? Well, in proper notation, that would be the probability that you have no cancer. And it says, so intersected with, it says that you do, so positive. Here's my joint probability over here on the end. We already know from my tree diagram, it's 0.0594. What is the probability that a randomly selected woman has a false negative? So this would be the probability that you have cancer and your test comes back negative. cancer, and negative. So this is this probability here. Joint probability. Which type of error is more serious? So just pause and think about that. Hopefully you recognize that a false negative is much more serious, because this is where a woman does have cancer, but you've just told her that she does not. So she's not going to seek any type of treatment, where it may be quite emotional to be told that you do have cancer, but then you would go on to further testing and it would be discovered that you do not. And finally, a randomly selected woman aged 40 or over from this population tests positive for breast cancer in a mammogram. Find the probability that she actually has breast cancer. So let's put this into notation to first help us see what they're asking, or how we can actually go about figuring it out. So the probability, it's asking what's the probability that she has cancer, but this is given that she tested positive. Okay, so test comes back, what's the chance that she really does have it? Use your conditional formula. This would be equivalent to the probability of cancer, I'm going to abbreviate, intersected with positive, over the probability that she tested positive. Again, that formula is on the formula sheet. This is equal to, our joint probability is right here from our previous tree diagram we made, 0.0097, divided by the probability that she's positive would be the sum of these two. So if I add those two together, let's see, that's 0.0691. And then I'm going to divide, that's approximately 0.1398. So approximately a 13.9 or approximately 14% chance that she really does have cancer if the test came back positive.